Hello. So this is a summary video of my balloon project, and I'm just going to take you through a brief but complete, more or less, history of my ballooning experiences. So the whole thing really started back in about 6th grade with this thing, which is exactly what it looks like. It's a hot air balloon made out of a plastic trash bag and an aluminum tin and some copper wiring here. And this tin would hold hand sanitizer, which we would set on fire and use to heat up the air in the balloon. And so that's really where the project started. And from there, we then went on to much grander, more serious experiments, doing things with actual helium balloons instead of just hot air balloons, and with much larger size balloons as well as equipment. But it all started with this, really.
Pictured here is my twin sisters and I holding one of our second generation balloons. So in the latter half of middle school, we made the transition from hot air to helium, which had the primary advantage of being flameless, so we could safely fly these outside, which we were never able to do before. Equally important was the addition of a small payload consisting of a GPS tracker and a camera. This allowed us to follow the balloon while it was in flight and recover it once it landed, as well as see what the balloon had seen through the eyes of the camera. And this system worked decently well and was incredibly fun for me, especially as a middle schooler, but there were two main issues with it. So the first was instability. Owing to the payload's incredibly light weight, all of the footage we got from it was very shaky and violent, and I'll put some up here so you can see what I mean.
Oh yeah!
Yeah, it hurts to look at, really, but I promise you we improve on this in the following years. Now, the other issue was with control. There was no way to program a flight path for this balloon or anything of that sort. The latex balloon was simply mounted onto a plastic tube with a hole in it, and so it would slowly vent helium as the flight went on, and eventually it would lose its buoyancy and descend. But beyond this, there was really no way to control how high the balloon went, which was something that we wanted to address with our next design. Anyway, to round off our section on the second generation of balloons, I will leave you with the conclusion of the flight, which you caught a glimpse of earlier, which, of all places, landed in a Home Depot parking lot. Enjoy! After the end of middle school, the balloon project unfortunately took a rather long hiatus as I became very busy with high school. When I finally had the time to revisit the project in junior year, I knew I wanted to go big. My goal for the third generation of balloons, so to speak, was to build something that would be trackable, that could travel for hundreds of miles at very high altitudes, and most importantly, could control its elevation with a valve. Now, to this end, we came up with this very basic balloon diagram that you can see here, and it retains all of the parts from previous years, but it now has a flight computer which controls a valve through a relay, as well as an altimeter, and it's all contained in an insulated styrofoam housing, which is important for withstanding the lower temperatures at high altitudes. We also came up with a more in-depth flight computer diagram, as you can see here, to help flesh out what would end up becoming the most important and complex component of this design. Before we get into the whole story of the design process, I just wanted to put this image up on screen to give you an idea of how the actual balloon turned out as compared to the balloon diagram that we showed you earlier. So here we have all of the same components pretty much. We have the latex balloon itself, and we have the valve, which allows the balloon to vent its helium and lose its buoyancy. We have the camera embedded in the wall of the styrofoam box, which will allow us to see what the balloon sees. And at last we have the payload itself, which is suspended from the balloon, and this payload contains all of the electronics that the balloon needs to function. So it has the flight computer, which controls the valve and allows us to program in a specific flight pattern for our altitude. We have an altimeter. It's not pictured, but it's on the other side of that box. It's taped to the outside. And we also have the GPS, which allows us to, of course, track the payload. So now that you've seen the balloon, I hope you can have a more concrete understanding of how it functions and what it's really like. Now we can move on to the actual story of the design process. We spent approximately 4 months from March to July constructing and testing our balloon. The construction phase went smoothly and steadily, but the testing phase was much more interesting. We started out with tethered test flights. We would get a reel of plastic string, and we would attach it to the balloon, and we would essentially fly it like a kite. On the second one of our tethered test flights, the tether snapped. Luckily, however, all of our balloon systems were on, and we were able to track and recover the balloon, much like we would in a real flight. And this was great. It proved to be a much more thorough and competent test of the balloon systems, and it gave us the confidence we needed to move forward to actual flights. And so, it did, however, necessitate some additions to the balloon's design based on things that we observed from the testing. So the following clip will detail both the final design of the balloon and any additions that were made because of this tethered test flight.
Camera's on. Alright.
After the very lucky success of our unexpected test flight, we realized that there were still several improvements that could be made to the balloon's design before it was ready for something longer range. And so the first and the primary change that we've made is that we've modified the software that our flight computer runs so that now it saves the data from the altimeter every 10 minutes rather than at the end of the flight as it did before. And so in the case of the power becoming disconnected, like it did for this flight after the balloon landed, the balloon will no longer lose all of the altimetry data that we had, and we'll hopefully be able to get a much more accurate picture of the flight now. In addition, our camera battery ran out about 10 minutes after it was thrown in the police car, as you saw in the footage. And so to fix this, we've got this rechargeable USB battery pack. It's 10,000 milliamp hours, and this will hopefully power this little camera here for double or even triple the time that it would have had before. In addition, we realized that the balloon must look quite strange and potentially dangerous to people who just see it falling out of the sky. And so we've made this little sign here that's going to be attached to the balloon's tether. And all the sign is telling you is that it's a harmless science experiment and please don't mess with it in any way. And we recommend that you call our number that's listed on the sign, and we'll give you a monetary reward for telling us where it is so we can recover it. In addition, we realized that visibility might have been a problem had it not been in the police impound. And so we painted it a bright neon pink here so that we'll be able to see it in much darker environments like among trees or something like that. And finally, we realized just how lucky we were with the way the flight played out. Because once it was recovered by the police, they put it in their impound, but it was face upwards. So the GPS tracker was able to acquire a signal. However, if it had been sideways or upside down, then we would never have gotten that signal and we would have completely lost the balloon. So for future flights, we have here this cell-based tracker. And so it's still a GPS tracker, but it communicates through cell towers, and so it doesn't matter what orientation the balloon lands in, this will still be able to get a signal as long as it's within range. And this perfectly complements the main GPS tracker because this communicates via communication satellites, and so this has a much wider range over the whole world, but it needs to be facing skyward the entire time. So other than that, the interior of the balloon payload is almost completely the same. So we still have the Arduino flight computer here. We have the altimeter on the outside. We have this relay that we use to actuate the valve. And we have this button that's used to start and stop the program that runs on this Arduino. And so now that we've made all these changes, we're confident that the balloon is ready for something much longer range. And so we've come out here to Omaha, Nebraska, because the surrounding lands are very, very flat and it should be very easy to recover. And tomorrow, we're ready to make our first long-range flight.
At last, we arrived in Nebraska. And in Nebraska, we made 4 flights over the course of a week. Now, the main goal of these flights was to prove that the balloon's altitude control system worked. This was by far the most unique and important feature of our balloon, and really what set it apart from all of the other stuff we had seen online. So this was incredibly important to us. And so the first 2 flights unfortunately failed due to programming errors. So the first one was a failure in the methodology of the code, and after fixing this, I forgot to change a single value, which of course completely broke the code for the second flight, and so the second flight also failed. Both of those flights overshot their target altitude and went too high and popped. Luckily, we were able to recover the payload on both of them. Now, the third flight actually undershot its altitude, and we believe this was because of a combination of an underfilled balloon and the balloon's flight starting in an updraft, which confounded the flight computer by making it think the balloon had more lift than it really did, thus causing it to vent more than it really should have. So that's the first 3 flights. And for the fourth one, we had run out of the smaller balloons we were using, and so we switched to a 600-gram balloon, which should, in theory, give us more leniency with how high the balloon could overshoot its target altitude. So the fourth flight was, unfortunately, another failure. However, when we looked at the altitude versus time graph after recovering it, we noticed a very noticeable downwards curve near the peak of the graph, indicating that the balloon was indeed slowing down at the time it popped. And we believe if the latex balloon itself had been able to withstand another 500 or so meters, the balloon actually could have done its job and descended properly. With the conclusion of flight number 4, we had used up all of our balloons, our time, and our helium, which meant it was time to pack up and go back to New Jersey. Now, we won't be able to make another flight for several months, but in the meantime, we will be busy revising the design of the balloon slightly. So we have ordered larger, higher flow rate valves that will allow us to achieve greater control of the balloon and hopefully hit those altitude targets that we had been so frequently overshooting before. And I think in the spring, with these new valves, we can have a lot of success in our flights, and hopefully we can deliver those to you in some very cool videos. Other than that, there's not really too much to say, so I'll leave you with this footage from flight number 2, and you can see the balloon popping at approximately 13,000 meters above sea level. So have fun.